This is chapter 6.3. In this section, we'll discuss the relationship of DTFT to the Z transform. Let's remind ourselves what is the definition of the Z transform. Here is an equation showing that we are taking xn from negative infinity to positive infinity, multiplying by z to the power of minus n, where z is the complex number. So z can take in any complex number in the whole complex plane. While in the DTFT, we are also going to take xn and we are going to multiply with a complex number. But in this case, the complex number only belongs to the unit circle. So e minus j omega n, omega is from minus infinity to infinity, the real, but the amplitude is 1, and we break this is equals to cosine omega n plus, or here is minus j sine omega n. By substituting different omega, we will basically get a circle. The unit circle is this. This is the real part of z and the imaginary part of z, and the unit circle is this circle that is with radius 1. Now, from this point of view, DTFT is a special case of the Z transform. In fact, DTFT is exactly the Z transform at this unit circle value. And we can do that when the region of convergence of the Z transform include the unit circle. Let's refresh on one of the examples we have used in the past, and x of n is an infinite sequence, geometric sequence, that is half to the power of n un, and basically it is like this. At time 0 it is 1, at time 1 is half, at time 2 is half to the power of 2, and so on and so forth, and goes to infinity. It is a causal sequence existing from 0 to positive infinity because of this un over here, and it will exponentially decay. Now we can take the Z transform of this, and by lookup table, this is the Z transform of this sequence. This is a causal sequence. We can plot this is the real part of Z, and this is the imaginary part of Z along here, and then this circle here is the unit circle of radius 1, and we have a pole sitting here. And because the sequence is causal, we can shade a circle of this radius and extend it outwards, and this extension is the region of convergence, and this region of convergence will touch the unit circle, showing that the system is stable if this is a transfer function. And it also shows that along the unit circle, x of z exists. So this along the circle is x of z at the unit circle. Since it exists, therefore it also shows us that the DTFT exists, since they are actually the same equation. So what we do is that we take x of omega and we let it equals to x of z and substitute z equals to ej omega. So all we are doing is we write the z here, and then we will now substitute different omega. So what does it mean by omega equals to 0 to 2 pi? Well, what you should think of is that, now let me draw for you the real part, this line, this vector, and as this vector is transversing to here, then this is theta. So basically when we go, this is the angle 0, and we can go all the way one round, and then when we go one round, this is 2 pi. So the angle theta is an anti-clockwise from this real line over here, anti-clockwise, and this is the theta we are talking about. So 0 to 2 pi is enough, because even if you do more than 2 pi, you are back to theta plus 2 pi, which is the same as theta. Now what about the values? The values of x of omega would be along this height. right? So therefore we will see that the values will be from this high value, and it will go down to a low value over here, and this can be visualized from x of z in this 3D plot. Again, x of z is a complex number, and we are only plotting the magnitude, okay, the magnitude in the log scale. Now the other relationship of x of z transform to the DTFT is this. Typically we are given a difference equation and we want to convert it into the transfer function first. So this guy is called a transfer function, and basically the transfer function, you use a difference equation and operate it such that this is equals to y of z divided by x of z. Now once you have the transfer function, we can extract the coefficients. So this coefficient is 1, this coefficient is 1, so this is 1, and minus 0.5 is here, this 1 is here. So we line up the coefficients from the highest to the lowest, and then we will write it as a vector and put the vector for the numerator coefficient as b and for the denominator coefficients as a. And once we have b's and a's, then we can use, of course, the FV tools of MATLAB to filter visualize this filter with these coefficients, and we can now see this is the, what do you call that? This is the pole and zero plot, and this is the region of convergence. We also can plot the impulse response. So just now you see it's half first, 0.5, 0.25, and so on and so forth. And of course we can also plot the magnitude and the phase response. So when you want to plot the magnitude and phase response, you realize that I am basically taking h of z and substituting e equals to j omega. Omega from 0 to 2 pi. So 0, in fact most of the time I plot 0 to pi only, because when you plot to 2 pi, there is a symmetry. The magnitude is of even symmetry and the phase is odd symmetry. So we only need to plot 0 to pi to get all the information that we want. Now how do you get DTFT of from h of z? Really simply taking z and substitute as ej omega. So z and ej omega. So we take the z, put it as ej omega. Z, put it as ej omega. The constants remain the same, and now we substitute omega from 0 to 2 pi, and we get a complex number. And from this complex number, we extract the magnitude, which is, I guess, is the, not sure whether it's the red or the blue, but one of them is the magnitude and the other one is the phase. Okay. So with that, I will continue the relationships in the next few slides. Thanks.